test mandated by Article 230.95 is generally conducted by a qualified electrician. It is essential that the individual performing this test possesses the requisite knowledge and practical experience to execute it in a safe and precise manner. There have been instances reported where electricians have encountered challenges or issues during these tests. These include false positives where the test erroneously indicates a ground fault when no such fault exists. This can stem from several sources, including background noise on the grounding conductor or a defective testing device. False negatives can also occur where the test fails to detect a ground fault that is genuinely present. This may be attributed to factors such as a high-resistance ground fault or, again, a malfunctioning test instrument. In some cases, there have also been reports of equipment damage as a result of the test, typically because the procedure involves applying a high voltage to the grounding conductor. To mitigate the risk of encountering problems or issues when performing the test stipulated in Article 230.95, several precautions can be taken. Firstly, ensure that a qualified electrician is employed to carry out the test. This electrician should possess the necessary expertise and experience to conduct the test both safely and accurately. Secondly, it is imperative to utilize a properly calibrated test instrument. Regular calibration ensures the instrument's accuracy, which is vital for reliable results. Thirdly, always adhere to the manufacturer's instructions for the test equipment. Deviation from these instructions can lead to inaccurate readings or even damage to the equipment. Finally, it is important to acknowledge the inherent limitations of the test itself. It is not entirely infallible, and there are scenarios in which it may fail to detect a ground fault that is actually present. The purpose of Article 230.95 within the National Electrical Code is to enhance electrical safety by mandating ground fault protection of equipment. This protection is specifically required for grounded systems rated 1000 volts or less, but more than 150 volts to ground, where the disconnecting means are rated 1000 amps or more. Ground fault protection systems are designed to detect ground faults, which are unintentional electrical connections between a live conductor and ground. These faults can create dangerous conditions, including electric shock and fire hazards. By detecting and interrupting ground faults, these protection systems minimize the risk of these hazards. The test required by Article 230.95 is intended to verify the proper operation of the ground fault protection system. This test typically involves injecting a test current into the grounding system and verifying that the ground fault protection system trips as expected. This ensures that the system is functioning correctly and will provide the intended protection in the event of an actual ground fault. To avoid false positives, ensure that the grounding system is clean and free of any stray currents or noise. Use a high-quality test instrument that is designed for testing ground fault protection systems. Follow the test procedure carefully and do not apply excessive test current. To avoid false negatives, ensure that the ground fault protection system is properly installed and configured. Verify that the system is set to the correct trip current and time delay. Use a test instrument that is capable of injecting a sufficient test current to simulate a ground fault. To avoid equipment damage, use a test instrument that is designed for testing ground fault protection systems. Do not apply excessive test voltage or current. Follow the test procedure carefully and do not exceed the manufacturer's recommendations. Understanding the functionality and testing procedures associated with Article 230.95 is crucial for electricians and electrical professionals to ensure the safety and reliability of electrical systems. By adhering to best practices and taking the necessary precautions, you can minimize the risk of encountering issues during testing and ensure that ground fault protection systems are functioning correctly. The qualified electrician performing the test should understand the theory and operation of ground fault protection systems. This includes knowing how these systems detect ground faults, how they are designed to trip, and the various factors that could affect their performance. Furthermore, they must be familiar with the relevant sections of the National Electrical Code, specifically Article 230.95, and any other applicable standards. The electrician should have hands-on experience performing these tests on similar systems. This experience allows them to anticipate potential problems, troubleshoot issues effectively, and interpret the test results accurately. The qualified electrician should also possess the necessary safety training and certifications to work on electrical systems. This includes training in lockout-tagout procedures, personal protective equipment, and other safety practices. When selecting a test instrument, ensure that it is designed for testing ground fault protection systems. The instrument should be able to inject a test current into the grounding system and measure the trip time of the ground fault protection system. It should also be properly calibrated to ensure accurate readings. Calibration should be performed regularly according to the manufacturer's recommendations. The test instrument should also be user-friendly and easy to operate. This will help to minimize the risk of errors during testing. Always follow the manufacturer's instructions when performing the test. These instructions will provide specific guidance on how to connect the test instrument, how to apply the test current, and how to interpret the results. Deviating from the manufacturer's instructions can lead to inaccurate readings or damage to the equipment. Be aware of the limitations of the test and understand that it is not foolproof. There are some cases where the test may not indicate that there is a ground fault when there actually is one. This can happen if the ground fault is intermittent or if the resistance of the ground fault is too high. If you suspect that there may be a ground fault even if the test does not indicate one, further investigation may be necessary. Remember that safety is paramount when working with electrical systems. Always wear appropriate personal protective equipment, such as gloves, eye protection, and hearing protection. Follow lockout-tagout procedures to ensure that the equipment is energized before you begin working on it. Never work alone and always have someone nearby who can assist you in case of an emergency. By following these guidelines, you can minimize the risk of encountering problems or issues when performing the test required by Article 230.95 and ensure the safety and reliability of electrical systems. Ground fault protection is essential for protecting people and equipment from the hazards of ground faults. Therefore, it is important to ensure that these systems are properly installed, tested, and maintained. Article 230.95 mandates ground fault protection for certain electrical services to enhance safety. It applies specifically to grounded wire electrical services operating at more than 150 volts to ground, but not exceeding 1000 volts. Where the service disconnecting means is rated for 1000 amps or more. This requirement is primarily in place to protect equipment from damage due to ground faults, as well as to reduce the risk of electrical fires. The principle behind ground fault protection is to detect unintended current flow from a hot conductor to ground. In a properly functioning electrical system, current should only flow through the intended circuit path. However, if a fault occurs, such as a damaged wire coming into contact with a grounded metal enclosure, a ground fault current will flow. This current can be significantly lower than the overcurrent protection threshold for circuit breakers or fuses, meaning that standard overcurrent devices may not trip in response to a ground fault. Ground fault protection systems are designed to detect these lower-level ground fault currents and quickly interrupt the circuit, preventing damage and reducing the risk of fire. These systems typically use a current transformer that encircles all the service conductors, including the neutral. Under normal operating conditions, the current flowing through the hot conductors is equal and opposite to the current flowing through the neutral conductor, resulting in a net current of 0. However, if a ground fault occurs, the current flowing through the hot conductors will no longer be equal to the current flowing through the neutral conductor. This imbalance creates a net current that is detected by the current transformer. When the detected current exceeds a preset threshold, the ground fault protection system trips the service disconnecting means, interrupting the flow of power to the service. This rapidly clears the ground fault and prevents further damage. The testing required by Article 230.95 involves verifying the proper operation of the ground fault protection system. This typically involves injecting a test current into the grounding system and confirming that the system trips within the specified time. The test is performed to ensure that all components of the ground fault protection system are functioning correctly and that the system will provide the intended protection in the event of an actual ground fault. Several factors can contribute to issues during ground fault protection testing. Firstly, improper grounding and bonding can affect the performance of the system. If the grounding and bonding system is not properly installed, it can create unwanted ground loops or impedance, which can interfere with the detection of ground fault occurrence. Secondly, electrical noise can also interfere with the system. Electrical noise can be generated by various sources, such as electronic equipment, lighting systems, and other electrical loads. This noise can create false readings or interfere with the detection of ground fault currents. Thirdly, incorrect settings can affect the system. The ground fault protection system must be properly configured with the correct trip current and time delay settings. If these settings are not properly adjusted, the system may not trip when a ground fault occurs, or it may trip unnecessarily. To avoid these issues, it is important to ensure that the grounding and bonding system is properly installed and maintained. All grounding connections should be clean and tight, and the grounding conductors should be sized according to the requirements of the National Electrical Code. It is also important to minimize electrical noise in the system. This can be done by using shielded cables, filtering power supplies, and grounding electronic equipment properly. Finally, the ground fault protection system should be properly configured with the correct trip current and time delay settings. These settings should be based on the specific characteristics of the electrical system and the loads it serves. Understanding the requirements of Article 230.95 and the principles of ground fault protection is essential for electrical professionals. By following proper installation and testing procedures, you can ensure that ground fault protection systems provide the intended protection and enhance the safety of electrical systems. The potential for false positives during ground fault testing can be influenced by several factors. One common cause is the presence of leakage current in the electrical system. Leakage current is a small amount of current that flows through the insulation of electrical equipment and wiring to ground. While a small amount of leakage current is normal, excessive leakage current can trigger a false positive. This can occur when multiple devices with small leakage currents are connected to the same circuit, causing the total leakage current to exceed the ground fault protection threshold. Another factor that can contribute to false positives is the presence of harmonic currents in the electrical system. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the electrical system. These currents can be generated by nonlinear loads such as electronic equipment, variable frequency drives, and switching power supplies. Harmonic currents can cause the ground fault protection system to misinterpret the current flow and trigger a false positive. The sensitivity of the ground fault protection system can also affect the likelihood of false positives. A highly sensitive system is more likely to trip in response to small variations in current flow, increasing the risk of false positives. Therefore, it is important to select a ground fault protection system with appropriate sensitivity for the specific application. To minimize the risk of false positives, it is important to address the underlying causes of leakage current and harmonic currents in the electrical system. This can be done by improving the insulation of electrical equipment and wiring, using harmonic filters to reduce harmonic currents, and selecting a ground fault protection system with appropriate sensitivity. It is also important to perform regular maintenance and testing of the electrical system to identify and address any potential issues that could contribute to false positives. Conversely, false negatives can also occur during ground fault testing, where the ground fault protection system fails to trip when a ground fault is present. This can be caused by several factors, including a malfunctioning ground fault sensor, incorrect wiring of the ground fault protection system, or a high resistance ground fault. The ground fault sensor is responsible for detecting the ground fault current and signaling the ground fault protection system to trip. If the sensor is damaged or malfunctioning, it may not be able to accurately detect the ground fault current, resulting in a false negative. Incorrect wiring of the ground fault protection system can also prevent the system from tripping when a ground fault occurs. For example, if the current transformer is not properly connected to the ground fault relay, the system may not be able to detect the ground fault current. A high resistance ground fault can also cause a false negative. A high resistance ground fault occurs when the ground fault current flows through a high resistance path to ground. This can reduce the magnitude of the ground fault current, making it more difficult for the ground fault protection system to detect. To prevent false negatives, it is important to ensure that the ground fault protection system is properly installed and maintained. This includes verifying that the ground fault sensor is functioning correctly, the wiring is properly connected, and the system is tested regularly. It is also important to address any potential sources of high resistance ground faults, such as corroded connections or damaged wiring. In some cases, the ground fault protection test itself can potentially damage equipment. This is more likely to occur when using older or improperly calibrated test equipment. The test typically involves injecting a controlled current into the grounding system to simulate a ground fault. If the test current is too high, it can cause damage to sensitive electronic equipment or wiring. Similarly, if the test equipment is not properly calibrated, it may apply excessive voltage to the grounding system, which can also cause damage. To minimize the risk of equipment damage during ground fault testing, it is important to use properly calibrated test equipment and follow the manufacturer's instructions carefully. It is also important to be aware of the potential for damage to sensitive electronic equipment and take appropriate precautions, such as disconnecting the equipment from the electrical system before performing the test. Furthermore, it is crucial to ensure that the person performing the test is qualified and experienced in ground fault testing procedures. They should be familiar with the potential risks and take appropriate safety precautions to prevent damage to equipment or injury to personnel.